So before we begin, let's remember the mappings between the analogy and the actual stack. So in the analogy, we had the set of instructions, step 3, step 4, step 5. This corresponds to the code for main here. So this is like the main set of instructions. And then in the analogy, we had this definition of how do you put things together. You put one thing in your left hand, you put one thing in your right hand, and then you put them together. That corresponds to the code for foo here. So that's the secondary set of instructions. In the analogy, we had this thought that we were thinking about before. So something about how I like pancakes that corresponds to the previous stack frame. So the stack frame of the previous function. In the analogy, we had these little pointers telling us what is the extent of my thoughts so far. And that corresponds to EBP and ESP here. So that tells us the top and the bottom of the current stack frame. And finally, we had EIP, which told us kind of like my place in the instructions. So maybe you had like a finger pointing at the instructions, telling you where you were there, and EIP represents that. And this is a bit of a late addition, but when I was making this video, I realized I've never actually explained what EBP, ESP, and EIP stand for. So just really quickly, the E just stands for the fact that this is a 32-bit architecture. So I believe in a 64-bit architecture, it would be RBP, RSP, and RIP or something like that. I don't remember exactly, but the E just means that this is a 32-bit architecture. And then the BP stands for base pointer. You'll see why in a couple of slides. SP stands for stack pointer, which makes sense because ESP always points to the bottom of the current stack, so it is a stack pointer. And IP stands for instruction pointer, which makes sense because it is currently pointing to whatever instruction we're executing. So the first thing we did in the analogy was we looked at the instructions. It said you need to use parts 34 and parts 27. So we made a note of that by remembering it. So that's what we have done here. We've just, on the stack in our memory, we've remembered that the second part is 27 and the first part is 34. So what does this actually mean for the stack? This means that we're going to push 2 arguments on the stack. So somewhere in main, it'll tell us what arguments we should be using, and we're going to push those arguments onto the stack. So one thing you do have to remember is that ESP should adjust to point to the new lowest value on the stack. So remember that ESP also serves the purpose of telling us what the lowest point on the stack is right now. Everything below that is undefined. So if I do want to remember these arguments, I need to move ESP down to the bottom of the arguments so that they're actually remembered. If I don't do that, then they're going to be like left floating off in the undefined section. Also notice that arguments are added to the stack in reverse order. Why did they do this? It's kind of like a compiler decision. Sorry if it's kind of annoying, but I do think there's like a nice use for them, as you'll see in just a little bit. But do notice that argument 2 was pushed first, so it has a higher address, and then argument 1 was pushed next, so it has a bit of a lower address. The next thing we want to do is, in the analogy, we had to remember where we were in the instructions so that after we're done putting stuff together, we know what the next step is. So that was kind of like adding into our memory a reminder that we need to do step 5. So that's what I've done here. Notice that there is this arrow here that like branches out of the step 5 and then points down in the code section. So this arrow is just kind of like reminding us that when we say after this do step 5, the step 5 is referring to the step 5 in the instructions. So what does this actually look like? This is the equivalent of pushing the current value of EIP onto the stack. Why? Because EIP is telling us where we are in the instructions. So if I push the current value of EIP, that'll tell us where we are in the instructions so that when we come back later, we'll know where we were in the instructions. And remember that as always, we need to adjust ESP to be the new lowest value. So again, I don't want this old EIP value to just be floating off in undefined areas. So I need to adjust ESP to make a note that this is something that I do want to remember. And again, this arrow is just kind of like a pointer. It just tells us that this old EIP is actually an address. We're actually storing an address, just like we're storing in the registers. And this address is the address of something in the code for main. So wherever we were in the code for main, that's the address that we put in the EIP. So there are a couple names for what we've just pushed onto the stack. So sometimes this thing is called the old EIP. So you might be wondering why it's called the old EIP, even though right now this value is pointing into main and EIP is also pointing into main. Well, the reason is because very shortly we're about to move into the code for foo, which means that EIP is very shortly about to move into foo. And so when that happens, when we're executing the function foo, then this value that is still pointing at main is going to be the old version of EIP. So right now it is the current EIP, but as soon as we move into foo, it will be the old EIP. Also, sometimes this value is called the RIP, which stands for return instruction pointer, because once we're in foo, this value is going to be the address that we're going to return to after foo is finished executing. So the next thing we did in our analogy was to make a note of our previous thought. So by now the pancakes are getting kind of far away, and so we made a mental note to ourselves that the last thing we were thinking about was pancakes. So this is equivalent to pushing the current value of EBP onto the stack. And why is that? Because right now EBP is pointing to the stack frame for main, and that is the equivalent of our previous thought. So if I push the current value of EBP, that's an address, and that address points to wherever my previous thought was located. And just like before, why are we calling it the old EBP now? It's because EBP is soon about to change. So when the new stack frame comes into effect, EBP is going to change. And when that happens, the value that you see now in the stack is going to have been the old EBP. And this value is sometimes also called the SFP, which stands for saved frame pointer, because we're saving a pointer to the previous frame. And finally, we're going to just adjust the stack frame. So this is the same in the analogy as like kind of focusing our thoughts on the pieces that we're about to put together. So what does this mean for the stack? It means that all three registers need to update. So by now, hopefully you're wondering, why did we not save ESP? The reason we didn't save ESP is because ESP is always going to point to the bottom of the stack, right? Every time you add a new value, ESP is always going to go down. Every time you remove a value, ESP is always going to go up. So because of the way we've designed this as kind of a nice coincidence, or because of the way they designed it, ESP will sort of naturally move down to where it's supposed to be. And when you're done, ESP will sort of naturally move back up to where it used to be just by virtue of you deleting all the things that you just pushed on the stack. So you do not need to remember the old value of ESP on the stack because ESP will naturally move with you down and move with you back up as soon as you're finished. But you did need to remember the old values of EBP and EIP because these two registers have changed. So a lot of things have changed, and now we're going to go through each one in some detail. So the value of EBP used to point to the top of the stack frame of main, and now it is pointing to the top of the stack frame of foo. And the stack frame is now not too well defined, right? Because I have all these weird things. I have the RIP, I have the SFP. So what does it really mean to be the top of the stack frame? For the purposes of the stack, or like this protocol, we've designated the top of the stack frame to be the old EBP. And this kind of like provides a nice way to remember it. So in normal execution, the EBP is always pointing to the old EBP. So that's kind of a nice way to remember things. ESP is now pointing to the bottom of the current stack frame. Now, where exactly is this? Why did I choose to leave two blanks here? This depends on how complex your function is. So if it was a very simple function, just a couple of local variables, I'd only want to drop ESP a little bit to make some space for the function. But maybe if it was a very complicated function, then I want to drop ESP a lot, so I have a lot of space in the stack frame to add local variables and do my work. And finally, EIP used to point in main, and now it's pointing in foo. And remember, once again, this is okay because I've saved the value of the old EIP on the stack. So now that everything is nice and set up, you're ready to do whatever the function instructions for foo said to do. This usually involves the local variables, which now you can put inside the stack frame. And remember how in the previous slide, we said something about how the arguments are pushed backwards? Well, now there's a nice side effect of that. And the side effect is that, remember that in C memory, the program is just seeing a whole bunch of bits. It's not seeing this nicely formatted grid. It can't see any of these arrows. It just sees a whole bunch of bits. So how does the program orient itself? Well, it uses EBP to orient itself. So remember that EBP is always constantly pointing to the old EBP. So what does this mean? It means that EBP is a nice little landmark to tell you where everything else is relative to itself. So that's also why EBP, the BP stands for base pointer, because it's kind of like the base, the landmark for where you find everything else. So in this case, if I want to figure out what the first argument is, it's going to be EBP plus 8 because I want to skip over the SFP, which is 4 bytes. I also want to skip over the RIP, which is 4 bytes, and I'll find argument number 1, which is 8 above. If I want argument number 2, that'll be 12 above. If I want argument number 3, it'll be 16 above, and so on and so on. So a nice consequence of pushing the arguments backwards is that now the first one is plus 8, the second one is plus 12, the third one is plus 16, and so on, which is nice. Also, the local variables are now going to be EBP minus 4, EBP minus 8, EBP minus 12, and so on. So EBP is just kind of like this nice anchor, this nice landmark that tells us where everything is. And finally, once your function is done executing, you want to put everything back where they were. And this is very nice because everything is already saved for me. So I know where to put the I know where to put the EBP because I had saved the value of the old EBP. I also know where to put EIP because I had a pointer to the old EIP. And then ESP, remember ESP is always pointing to the bottom of the stack. So as I clear up the memory and as I delete all the stuff that I don't need, ESP is just going to very nicely naturally move back up to where it used to be. So as I just said, ESP is going to naturally move back to where it is, and this usually involves popping a lot of values off of the stack because now we don't need them anymore. So one thing you do want to note here is that all the data I just wrote onto the stack is still there, so it's not going to be blanked out or anything. And the reason for this is because C is fast. There's really no need to blank any of this stuff out, so C does not. Also notice that ESP is now pointing pretty high up. Everything below ESP is undefined, right? So technically all that stuff down there is undefined anyway. So we're not really deleting it. We're just kind of moving ESP up, and that is the same as pretending it doesn't exist. One last quick note in this video, a lot of people get confused about structs in this class. So a struct is really just a group of variables bundled together. So you can think of it as just one big variable with a lot of smaller variables inside of it. So in this case, I have a struct cat, and it just has two variables inside, a character array and an integer. So inside a struct, the variables are always going to be filled from the bottom going up. So for example, in this case, the first variable in the struct is name, so that's going to get the lower address. And then the second variable is age, so that's going to get the higher address. If I had a third variable after that, it would get another higher address. If I had another variable after that, it would have an even higher address. So even though this struct is on the stack, within the struct, things are going to go from the bottom up. But let's say if I had two structs and I wanted to push two structs onto the stack, the first struct would still be higher than the second struct. So this is kind of hard to wrap your head around, but just remember that inside a struct, things go from the bottom up. And then besides that, the struct basically acts as a variable. So the stack itself still works the exact same way.